Today we're going to be proving Heron's formula through triangle area and algebra. Heron's formula stating that the area of a triangle can be found given its three sides being the square root of its semi-perimeter multiplied by, in this case, the semi-perimeter minus a multiplied by the semi-perimeter minus b multiplied by the semi-perimeter minus c, with its semi-perimeter being the perimeter divided by 2, in this case a plus b plus c divided by 2. From Pythagorean theorem we can find b1 squared plus h squared is equal to a squared. b2 squared, likewise, b2 squared plus h squared is equal to c squared. And finally, b1 plus b2, the two segments sum to be b, the side length for the triangle ABC. Therefore, we can call this equation 1, equation 2, and equation 3 respectively. Subtracting equation 2 from equation 1 to get b1 squared minus b2 squared, the h squared terms cancel out, is equal to a squared minus c squared. b1 squared minus b2 squared is written in the form of a squared minus b squared, factoring that to be b1 plus b2 multiplied by b1 minus b2 is equal to a squared minus c squared. From equation 3, we know b1 plus b2 is equal to side length b. Rewriting this as b1 minus b2 is equal to a squared minus c squared divided by b. We can combine this with equation 3, which states b1 plus b2 is equal to b. Calling this equation 3, calling this equation 4. We add the two together to cancel out the b2 term to get 2b1 is equal to b in the denominator and a squared minus c squared plus b squared as its numerator. Divide 2 on both sides to get b1 is equal to 2b in the denominator and a squared minus c squared plus b squared in the numerator, unchanged. Written b1 in terms of ABC that we're going to be using for a triangle's area formula, which states that the area of a triangle is given through area is equal to half multiplied by its base multiplied by its height. We can find the triangle's height through equation 1, but we use equation 1 and not equation 2, as it also has the h term in it, because we want to write h squared in terms of b1 squared, which has been defined through the side lengths of a, b, and c respectively previously. Therefore, rewriting this as h squared is equal to a squared minus b1 squared, taking the positive square root to be a squared minus b1 squared square rooted, and we take the positive square root as we know a triangle's height cannot be negative. So we can move this over to the right hand side to use as a reference for our area. This will be equal to half multiplied by its base side length, which is b, multiplied by its height, substituting it to be square root of a squared minus b1 squared, which is equal to half minus, or multiplied by b, multiplied by the square root of a squared minus b1 squared, which b1 is equal to a squared minus c squared plus b squared divided by 2 squared, 2b. This would be 2b, which is then equal to half b multiplied by the square root of, we give a squared a denominator of 4b squared to be 1 over 4b squared times a squared minus 4b squared, with its numerator being a squared minus c squared plus b squared squared. From this, we can factor 1 over 4b squared, as both terms have a common denominator of 4b squared. So this becomes half b multiplied by the square root of 1 over 4b squared, now factored out to be 2ab squared minus a squared minus c squared plus b squared squared. And we see that 2ab squared minus parentheses a squared minus c squared plus b squared squared is written in the form of a squared minus b squared. Therefore, factoring it to be half b multiplied by the square root of 1 over 4b squared multiplied by 2ab plus a squared minus c squared plus b squared multiplied by 2ab minus a squared plus c squared minus b squared, which we can combine the terms within the parentheses to be a squared plus 2ab plus b squared, which we all know as a plus b parentheses squared. This becomes a plus b parentheses squared minus c squared multiplied by, factoring out the negative sign to be a squared minus 2ab plus b squared and parentheses plus c squared, which can be equal to half b multiplied by the square root of 1 over 4b squared multiplied by, this remains unchanged as parentheses a plus b squared minus c squared and parentheses multiplied by the negative of a minus b squared plus c squared, which once again we have written in the form of a squared minus b squared. The term a, in this case being a plus b, the b being c, and within here, c being the a term and b being the a minus b term, which are in the form of a minus b squared, a squared minus b squared, factoring that out to be 1 over 4b squared multiplied by a plus b minus c multiplied by a plus b plus c multiplied by c minus a plus b multiplied by finally as c plus a minus b. From here we can plug in half b into the square root, but in order to apply that into it, we must square 1 over 2b as a whole. So this becomes, after canceling out like terms, to be 1 over 16 multiplied by a plus b minus c multiplied by a plus b plus c multiplied by c minus a plus b multiplied by c plus a minus b. This equation remains unchanged. And now, from this point, we can introduce our assumption. Let the variable s be 2 in the denominator of a plus b plus c, in other words, the triangle's semiperimeter. But how do we relate the semiperimeter with these terms right here, a plus b minus c minus a plus b, and c plus a minus b, as they are not written in the form of the semiperimeter? Well, that's an easy fix. As we know, a plus b minus c divided by 2, which is equal to its semiperimeter minus c, as is equal to a plus b plus c divided by 2 minus c to give us 2 in the denominator, a plus b minus c. So this checks out. But how did I get a plus b minus c divided by 2? Well, we know 1 over 16 is equal to 2 to the 4th power. We can distribute the 2 to each of a denominator for each terms. So a plus b minus c divided by 2 multiplied by a plus b plus c divided by 2 multiplied by our next term, which is c minus a plus b divided by 2 multiplied by our last term, c plus a minus b divided by 2. So we have proven a plus b minus c is equal to the semiperimeter minus c, which we substitute into the square root to get s minus c. We see the second term, a plus b plus c divided by 2, being the same as the semiperimeter definition, with the third term being equal to s minus a, the fourth term being equal to s minus b. And we do that for the likewise process that we did for a plus b minus c divided by 2, which we can then rearrange within the square root to get the semiperimeter multiplied by the semiperimeter minus a, s minus b multiplied by s minus c. The exact same formula for Heron's formula, thus proving it as true.